The reason that we get into limits is to help us describe graphs. Why do we need to describe graphs? Because really what we look at a lot of times is whether graphs are continuous, what's happening, things like that. So there's a lot of background stuff in this first chapter. And a big one that we'll use all year long is this whole idea of continuity. Continuity, what does that mean? Continuity is something continuous. Can I draw, how about no breaks? And the test that I like to use is, can I draw this thing without picking up my pencil? And I can't draw a hole in the graph. I can't draw a break in the line. I can't draw an asymptote without picking up my pencil. So can I draw it without picking up my pencil is kind of our layperson's definition. So what we have to do is we have to make the assumption that functions will be continuous unless we find an exception, and that's really what's going to happen. Most functions are continuous most places, especially the ones that we deal with, but we need to look for exceptions. That's really what we're trying to do. So some exceptions. F of c doesn't exist, does not exist. Well, so what that would mean is if I go to, let's say, c, we're going to call c that generic x value. Functions will be continuous at x equals c unless we find one of these things. So let's say I have a graph that looks like that. Well, what would that mean? Well, that would mean when you put x equals c into the function, try to evaluate it, your value wouldn't exist. So what do we really have here? We really have a hole in that graph. Second example, let's say I put x equals c right here again, whatever that generic x value is. Limit as x approaches c of my function does not exist. Well, we've already done enough talking about limits. Well, that would mean that the limit as x approaches c from one side doesn't match the limit as x approaches c from the other side. Now, one of these has probably got a dot on the end, one has probably got a filled circle on the end, or maybe not. But the idea would be we'd like to call that, I've had previous classes that have called that a clap and miss, meaning I try to clap and they're headed toward two different places, so my limit's not going to exist. So there's a second type of discontinuity. And then the third one, well, what happens if the limit exists, but it doesn't match what f of c is? So let me throw c on here again. And let's say that f of c, in this case, is the number 6, y equals 6. Okay, but then the limit as x approaches c exists, meaning they're headed toward the same place from either side, but that place they're headed toward doesn't match what I get when I plug c into the function. So again, another example of a discontinuity. So what happens if part A, f of c doesn't exist? And by the way, this could also be a vertical asymptote. That could happen for part A. Part B, the limit as x approaches c doesn't exist. That's pretty much exactly what I have drawn there, one side or the other. It could happen on either side of a vertical asymptote. And part C, what happens if the limit exists, meaning they're headed toward the same side, but it doesn't match what I get when I plug c into the function. So those are your three major types of discontinuities. And then what we want to do is we want to get into some specific terms. Removable discontinuity is a hole. A hole. And to think about it algebraically, a removable discontinuity is a limit that direct substitution won't work for, but that you can overcome using some of those techniques that we've seen the past few lessons. So a removable discontinuity is a hole in the graph. A limit that you can't directly substitute into it first, but you can fix based on how you manipulate the equation. A non-removable discontinuity is a vertical asymptote, a break, a jump, a clap and miss, whatever you want to call it, a vertical really anything else. So in the graphs that we have up here, a removable would be A, because it's a limit that I could overcome. A limit exists, but the function's goofy. This one would also be a removable discontinuity. And then this one in the middle would be a non-removable discontinuity. And if I had thrown in the idea of the vertical asymptote, that vertical asymptote up there would also be a non-removable, because we really can't overcome it. So any kind of hole in the graph is removable. Anything else is not. Okay, so some continuity. Let's see what we can do with some of this. So are these functions continuous? Well, the first thing that I would look at, f of x equals 1 over x, maybe it's a graph you remember, maybe it's not. I think what you're going to notice first is that x can't be equal to 0. Well, if x can't be equal to 0, then that function's definitely not continuous because I can't plug 0 in and get a value. So this thing would be discontinuous at x equals 0. And if we did punch it in, or we did remember that the graph of f of x equals 1 over x looks something like this, and that's a very rough sketch of what this graph would look like, we're going to see that we have a vertical asymptote at x equals 0. That would mean it is a non-removable discontinuity. So it's discontinuous at x equals 0, and it would be non-removable. Second one, g of x. Well, according to this, I'm looking at this thing originally, and it looks like x had better not be equal to 1 because that would make this function undefined. But if I did the limit as x approaches 1 of this function, I would take the numerator and factor it into x minus 1 and x plus 1. In the denominator, I've already got x minus 1. Well, if I simplify, I can cancel the x minus 1s. Now my direct substitution is going to work, and by direct substitution, I'm going to get y equals 2. So that would be the result of my limit. So here's what we've really got going. This graph, limit as x approaches 1 of the quantity x plus 1, direct substitution takes me up there. Here's what you're going to find. If you were to punch in this original g of x function, what you would see is y equals x plus 1. Y equals x plus 1. Well, y equals x plus 1, let's see, that would have a y-intercept at 1, and it would go up 1 and over 1, up 1 and over 1, up 1 and over 1. If I'm trying to make a decent graph here, it would end up looking something like this. But here's the tricky thing. This graph that really looks this way actually can't exist at x equals 1 because of the original equation. So what we're really going to have is we're really going to have the equation y equals x plus 1, but it has a hole in it at the place that this function doesn't exist. So here's a way that we just got to an equation that showed us one of these removable discontinuities like A or C, but now as I glance at this thing, what I'm going to find, this graph is really just y equals x plus 1, but it has a hole in it at the place that g of x doesn't exist. So this thing is discontinuous at x equals 1. It would be removable, and I would know, based on figuring out this limit, that the place that this thing is technically discontinuous, there's a hole at the point x equals 1, y equals 2. So in successfully overcoming this limit, I would find out where the hole in the graph is. So problem number 1, non-removable asymptote. Problem number 2, removable hole in the graph at x equals 1. Finish the limit, y equals 2. The last one I want to add in this particular setup, or I guess we'll do these two. H of x equals sine of x. We've done a lot of work on this already. Continuity, sine graph. I could keep going on and on and on. Does that function have any breaks, any holes, any asymptotes? Absolutely not. This is a, whoops, I don't know how to spell continuous. This would be a continuous function, based on what we know about the graphs. And then this last one, find A so that this f of x is a continuous function. Well, what's it going to take to make a continuous function? Long story short, this function is splitting at x equals 2. So we need to make sure that the limit as x approaches 2 from the left-hand side, meaning using the x approaches 2 from the left-hand side would be the top example. So we'd use 3x squared. Well, if I did that limit, I could do direct substitution. 3 times 4 would give me a 12. If I then check the limit as x approaches 2, from the right-hand side would be that bottom equation because the x's are bigger than 2. Then I do the limit as x approaches 2 of ax, and that would give me 2a. Well, in order for this function to be continuous, approaching 2 from either side would have to match. So what I would do is I would take this 12 and set it equal to that 2a, and I would solve. and I would find out that if a was equal to 6, I would have a continuous function. Prove it to yourself. If you plug 6 in place of the a, 6 times 2 is going to be 12 when I go and carry out that limit. So there's an example of continuity and dealing with and how it applies to limits.